So, we start with another topic on the neutral point clamp converter, which is called the midpoint balancing or the capacitor voltage balancing of the 3 level neutral point clamp converter. So, this is a topic. So, first we will understand why the midpoint voltage of the NPC fluctuates during the operation of the converter. First we will understand, and subsequently we will see two techniques of mitigating this issue. So, the first technique will be kind of the second technique is a superior technique to the first one, and we will see how this works, these two techniques work. Now, this is a subject which has there has been a lot of research on this subject, and you can also find a lot of literature, and also it is discussed in several books. So, there are a lot of material available. So, let us start what it is. So, if you see here the topology of the 3 level NPC, we find that there are two capacitors which are present in the DC bus, and the midpoint of this DC midpoint of the two capacitors, that is this point O, is utilized in this converter. The midpoint is needed because we would like to have 3 levels of voltage. VAO should have 3 levels of voltage, Vd by 2, this one 0 and minus Vd by 2. Okay. So, that is why we need this midpoint. However, during the operation of the converter, the midpoint voltage is also sometimes called the neutral voltage. The neutral voltage or the midpoint voltage is fluctuating. Okay. It is not constant value. We expect the neutral voltage or the midpoint voltage to be perfectly constant, but it will fluctuate due to the operation of the converter. And why will it fluctuate? It will fluctuate, you can readily understand from here that whenever we access the 0 voltage from the converter, that means whenever we are impressing the 0 voltage at point A with respect to point O, then we are accessing this midpoint. Okay. When the VAO voltage is Vd by 2, then we are kind of like accessing the positive DC bus. When VAO is negative, we are accessing the negative of the DC bus. Whereas, when we are putting a level of 0, then we are accessing the midpoint. Okay. And during this condition, the current is drawn or current is injected into this midpoint, and that is why there will be a net charge flowing out or in to this midpoint, which is the reason why the midpoint voltage will fluctuate. Okay. So, normally we will see over time that there is an AC oscillation on the midpoint voltage, okay, which it depends on which type of switching sequence and what is the switching frequency at which we are operating. The magnitude of the AC oscillation will vary. So, if it varies, then if the variation is substantial, normally if the variation is very small, then we can still go on with the operation of the converter. However, if the midpoint fluctuation is very large, or if there is some fault has happened, or if there is an unbalanced operation of the converter, then this midpoint voltage can substantially deviate from 0. Okay. So, so far throughout the analysis of the converter, so far we had said that the 0 point, this O point is always at 0 potential, but actually it is not so. So, there is a fluctuation. So, if this fluctuation is very high, okay, then what can happen, that it can go more than the device rating. So, see, in this converter all the devices are rated for Vd by 2. Okay. However, if this point's voltage, so the total DC bus voltage is Vd. So, this capacitor is Vd by 2, this capacitor has a voltage across it Vd by 2, and that this capacitor also Vd by 2. Okay. Under ideal condition, when there is no fluctuation in the midpoint voltage. However, if one of the capacitors is charging up, that means the other capacitor is, the voltage across the other capacitor is falling. Okay. If voltage across one is going up, the voltage across the other is falling down, given that the total DC bus voltage Vd is constant. So, if that happens, whenever we do the switching, the voltage stress on the switches which are off can be more than Vd by 2. Okay. And if that happens, then basically we are crossing the voltage limit, or we are crossing the device rating, voltage rating of the device, right. So, it can be more than Vd by 2. We have started our design assuming that all devices or these capacitor voltages are exactly at Vd by 2, and accordingly we will choose our devices of having a voltage rating of Vd by 2. But if this midpoint voltage O fluctuates or goes up or down, then the device rating, so this voltage across the device can be more than the voltage rating of the device. So, that is not a good practice. And also, if the 0 point volt of this midpoint voltage is fluctuating, then the harmonic performance gets degraded, okay, because we expect 3 levels of voltage, and these 3 levels should be distinct and equal, okay, plus Vd by 2, minus Vd by 2 and 0, and those voltage levels Vd by 2 should be equal in magnitude, then only we get all the symmetries of the waveforms and we get a very good harmonic performance. However, if the DC bus voltages are unequal, then we get poorer harmonic performance, especially lower order harmonics can come into the voltage, which is not desirable. Okay. So, therefore, the midpoint voltage must be kept within a certain limit. Okay. The midpoint voltage fluctuation should be kept within a certain limit. So, first we will see why the midpoint voltage fluctuates. Okay. In order to understand why the midpoint voltage fluctuates, we will analyze sector 1, and in this sector 1 we will see these switching states, and we will see what is the effect of these switching states on the current which is drawn from the midpoint. Okay. So, let us study the sector 1, and let us first see this vector plus 0 0. Okay. So, sorry, this switching combination plus 0 0 of a one small vector. Okay. So, when the switching combination plus 0 0 is used, this means that the A phase is connected to the positive DC bus and B and C phases are connected to the midpoint or the 0 voltage potential here to the point O here. So, this is the circuit. So, these are the 3 loads and where the 3 currents IA, IB, IC are flowing, and when we are applying plus 0 0 from the converter, then this is how the converter circuit looks like, assuming all the transistors and the diodes are ideal. Okay. So, you see here that the midpoint current I 0, yeah. So, this is equal to I b plus I c. Okay. So, you have plus here coming plus here and 0 and 0. So, this is the switching state. So, the I 0 current is I b plus I c. So, the midpoint current is I b plus I c, and if I a plus I b plus, and so since in this case the load is isolated, so that I a plus I b plus I c is 0. So, therefore, I 0 is equal to minus I a. Okay. Right. So, now if I a is greater than 0, for example, at any instant of time where we are applying this plus 0 0 switching combination for the small vector, at that instant of time, if I a is greater than 0, then what happens? Then it means that this current I 0 is basically the current is entering into the midpoint, because I 0 is equal to minus I a, and if I a is greater than 0, it means the current is entering into the midpoint. Okay. So, the current is flowing like this here. Okay. So, the current is flowing like this, the current is flowing like this, okay, in the midpoint, through the midpoint. So, which means that the capacitor C1 is discharging, and this point's potential, the midpoint potential V 0, this point's potential with respect to the negative DC bus will go up, because the total DC bus V d is assumed to be constant. So, if C1 is discharging, that means the voltage at the point O will go up. Okay. So, it will go on increasing, right. Now, take the other case, okay. Take the other switching multiplicity. So, you take this 0 minus minus. Okay. So, we have seen what happens with plus 0 0 multiplicity. Now, let us see what happens with 0 minus minus. So, 0 minus minus multiplicity or switching means A phase is connected to the midpoint, while B and C phases are connected to the negative of the DC bus, right. So, in this case I 0, you see I 0 is equal to I a and is equal to minus of I b plus I c, okay, like this. Now, if I a is greater than 0, same case as before, if I a at that point of time, if I a is greater than 0, then what is happening? C 2 is discharging. Okay. So, if I a is greater than 0, the current is flowing like this, the current is flowing like this, and hence C 2 is discharging, right, and therefore, midpoint voltage will go down, okay, assuming the total DC bus voltage is constant, right. So, therefore, we see that for the same value of I a, okay, for the same value of I a, these plus 0 0 and 0 minus minus, that is these two switching multiplicities of the small vector are producing a complementary effect on the midpoint voltage or on the capacitor voltage. Okay. So, in one case the midpoint voltage goes up, that is here. So, the midpoint voltage is going up, and in the other case the midpoint voltage is going down. Okay. So, if we apply these two small vectors in such a way in a switching cycle, so that they are of equal duration, so then we can ensure that due to this vector with two multiplicities, the midpoint voltage can be made almost, the midpoint voltage fluctuation can be made almost equal to 0. Okay. These two states can be applied for equal duration of time to make the midpoint voltage equal or midpoint voltage fluctuations to be 0. Okay. So, this will happen for this small vector here. Let us consider another small vector with plus plus 0 and 0 0 minus combination. I mean that this vector here plus plus 0 and 0 0 minus this vector. So, let us see what is the effect of this vector with these two switching multiplicities on the midpoint voltage. So, for plus plus 0 combination, how is the circuit looking like? So, which means plus plus 0 means A and B both are connected to the positive DC bus, whereas 0 means the C phase is connected to the midpoint. Okay. So, this is the circuit here, right, and the I naught current is equal to I C, which will be equal to minus of I B plus I A, right. So, therefore, during if I apply this vector here, if I apply this switching state and if I C is greater than 0, then we see that the current will flow like this here, which will cause C1 to charge up, and hence if the total DC bus voltage is constant, then the midpoint voltage will go down, right. On the other hand, let us take the other multiplicity 0 0 minus that state. In 0 0 minus, A and B phases are connected to the 0 point, while C is connected to the minus point. So, if again we assume that we have the same value of I C, okay, so then the midpoint current for 0 0 minus is minus I C. You can see here I 0 is I A plus I B and is equal to minus of I C, right. So, if this happens, then V 0 or the midpoint voltage is going to go up. Okay. So, here also for this small vector also we see that these two switching multiplicities have complementary effect on the fluctuation of the midpoint voltage. Okay. So, in general we can say that all small vectors which have two multiplicities, they have a complementary effect on the midpoint voltage. Okay. Now, let us see the large vectors. Okay. So, there are in that sector there are two large vectors plus minus minus and plus plus minus. Okay. When you apply any large vector, then the midpoint is not accessed. Say you can take the example of this plus minus minus for example. So, then you have plus minus minus means A phase is connected to the positive of the DC bus, while B and C phases are connected to the negative of the DC bus, right. So, you see here in this switching combination the midpoint is not accessed. So, there will be no fluctuation of the midpoint voltage, wherever it was there, wherever it was wherever the voltage level was, it will remain there only. So, this is the plus minus minus circuit. Similarly, if you take this plus plus minus circuit, you will see that the midpoint voltage is again not accessed. So, we say that in general large vectors will not affect the midpoint voltage. Okay. What will happen with the medium vectors? Okay. So, let us take this plus 0 minus combination. Okay. The medium vector which is this one on the space vector diagram, this one, this is the medium vector. So, plus 0 minus. So, what is its effect on the midpoint voltage? So, with plus 0 minus we see that there is a 0 accessed here. So, of course, this means that there will be a fluctuation, okay. And the circuit here plus 0 minus means the plus means A phase is connected here, B is connected to 0 and C phase is connected to minus. And so, the midpoint current is given by the phase current B. Okay. And so, whatever is the magnitude and direction of the B phase current, the midpoint voltage will fluctuate accordingly. Okay. Now, the middle vector or the medium vector, you see here there is no multiplicity on the medium vector, and so if this medium vector is used, okay, so it will cause some fluctuation in the midpoint voltage or the capacitor voltage. However, it cannot, so it must be compensated, but there is no multiplicity on this vector unlike the small vector. So, this midpoint, so this medium vector is something which must be taken care of, because it will cause a voltage to fluctuate, but in that sector, suppose in sector 1 there is no one to compensate that. Okay. So, there is no switching state which can compensate the effect of the middle vector or the medium vector. So, it must be done through some other technique which we will see. So, summarizing this whole thing, what happens in sector 1, we see that the 0 vectors, of course, the 0 vectors will have no effect on the midpoint voltage. Okay. The small vectors will have some effect, but the good thing is these small vectors have multiplicities, which if we can cleverly use these multiplicities for equal duration, then it is possible to compensate the fluctuation in the midpoint voltage. The problematic one is the medium vector, because it changes the midpoint voltage, but there is no vector because it has no multiplicity. So, it must be compensated. So, the midpoint voltage must be compensated by some other means which we will see, and large vectors have no effect on the midpoint voltage. Okay. So, now, so apart from that, so we have to develop some switching strategies to compensate the midpoint voltage fluctuation. So, there are many reasons of midpoint voltage fluctuation. One, we saw that if we choose the switching states, then with the multiplicities, then it causes the midpoint voltage to fluctuate, as we had just explained. But unbalanced operation, unbalanced 3-phase operation can also cause, and there may be also capacitor manufacturing tolerances, okay, non-idealities in the capacitor, or there may be also certain sudden deviation of capacitor voltage due to some unforeseen circumstances. So, if those things happen, then the midpoint voltage will suddenly, it may go away from the 0 potential which we had throughout assumed. Okay. If that voltage deviation happens, then the midpoint voltage should be brought quickly inside a permissible limit or near to the 0 level again. Okay. There may be a small fluctuation, say 2 to 5% is okay, but there should not be a large deviation of point of this voltage at this point away from what we have assumed to be 0 potential. Okay. So, we will now see some of the techniques to balance the midpoint voltage.